Hey, Jim. Nice to see you today. How are you doing?
So far, so good. Thank you, Kwabena.
Thanks for taking the time to meet with me, Jim. So, hi, I'm Kwabena, the president and co-founder of OpenMV, and today I'm talking with Jim Yastic. He's the director of technical marketing at Macronix.
Yeah, good morning.
Yeah, so Jim, tell me a little bit more about Macronix. Like, your company makes Flash, and you guys have been in business for a very long time, selling chips back since the original Nintendo, correct?
That's right. Yeah, we've been around for about 30 years, and our focus, in simplistic terms, is we do non-volatile memory. So we do different forms of it. We do eMMC to NOR flash to NAND flash. And even moving into other arenas like SSDs. So think of anything that involves non-volatile flash, and we're involved in that.
Well, non-volatile flash, yeah. It's a funny chip. I mean, these things are, the people don't think about flash too much, but it actually matters a lot for your ability to run new AI algorithms, which is what we're, talking with Macronix today about. So, flash chips pretty much are where we are storing models now in this new future, where you can execute these models in place out of. And the ability to do that is what gives us kind of like controls our speed for being able to run high throughput AI. And so it's pretty fascinating about these little chips, what they're capable of doing, what kind of performances they offer, and how they really tie into a new future where we're able to basically put an ML model on them and execute that in place.
Yeah, yeah, you're right. They're ubiquitous, and they've been around a long time. And you'll find them in every single application, just about every single application across markets. If you look at our focus, like any non-volatile memory flash vendor, we cover all the markets. We're involved in all of it, and AI, I think, is, as you've mentioned, is the most exciting for us because because it's so relevant, right? If you look at emerging applications, and AI really is I think right now front and center. I mean, yeah, there's a lot of hype, but there's a lot of real application development happening, and I think that OpenMV is a good example of that. And so, my job as in technical marketing is to understand what those challenges are and work with partners around the world to align our roadmaps and to ultimately provide system solutions that are going to work for the products you're developing, right? And so I think that probably in the near term, what we're most focused on is octal flash, and so comparing that, say, with single, dual, quad, octal, but octal's been out for several years now. But what we're finding is in AI on the edge and in nodes, we're finding that it's being used in a dual octal configuration, and it's pretty interesting, and it's actually accelerating pretty quickly in terms of what that adoption is. And so me and my team, we're spending a lot of time understanding those requirements and trying to, again, form fit the right solutions.
Yeah, I just like to back up for a second, just talk about AI for on the edge devices wasn't really big previously. This is starting to take off now. We'll go into some demos actually showing folks what you can do. But we saw this growth in performance of flash chips. I mean, back in the day, it used to be just a SPI chip, right? And then you went to quad SPI and then octal SPI. Like, do you have any thoughts about this growth? I mean, it wasn't AI before. Was it GUIs, right? Like that was the focus?
I think what was driving it, because I've been, I was a firmware engineer decades ago. I've been in this business a long time, and for example, when you hear about AI, I'm like, well, anytime you computerize something, it's some form of AI, So I think that if you look at the evolution of applications over the decades, What's really driven the evolution of Flash has been, I'm going to say, more code being applied to an application, but also the performance requirements. When you start to move to video, for example, there's a lot more. The performance envelope is greater, right? So, and then if you move to, say, data center, something like that, well, that's a big step function, in performance and so forth. So it really depends on the application, depends on the market, but it ultimately is driven performance, and it's driven density, and it's also driven a voltage, because voltage VCC has dropped. It continues to drop. It used to be 5 volts, then it went to 3 volts, and now we're at 1.8 volts, and that's the sweet spot. But where it's really going now is 1.2 volt and ultimately a 0.8 volt, and that's being driven by these SoC vendors. Their technology nodes continue to shrink. They're looking to simplify their design and the voltage rails, the number of voltage rails they need to support, and then LPDDR or LDDR and other peripherals that are using lower VCC voltage. Well, that in turn is driving lower VCC voltages or Flash. So you can kind of see the evolution and how our memory has changed. The technology hasn't changed, but these densities and performance and interfaces have changed.
Yeah. And so part of the reason I wanted to get on the call and talk with Jim today is just to show off something new that we're doing with OctoSpy Flash, actually, and to talk about the future of where things are going. So my company, OpenMV, we're introducing a new AI camera that uses Macronix Flash chip, and it's called the OpenMV Cam AE3. And so this little guy is, let's see if we can get it in focus. My camera can autofocus, but there's no way to actually tell it to do that. It just decides. There we go.
There you go.
Yeah, so this little guy here is 1 inch by 1 inch, ultra tiny. And as you can see there, we've got the Macronix Flash attached right next to it. So what's magical about this device is that the center chip is something called the Aleph Ensemble. This is a new microcontroller that draws only 30 milliamperes at full power. And it features about 13 megabytes of RAM on chip, clocked at about 3 gigabytes a second. So very, very high performance internal on-chip memory. And it offers 2 neural network processors that have a combined throughput of about 250 gigaops a second. This allows it to run like YOLO V5 models at about 30 FPS, meaning this little device, the size of a quarter, it draws 60 milliamperes at 5 volts in total, so 2.5 watts for the entire system. This thing can run YOLOs, YOLO, which is an object tracking model, human body pose, facial landmarks, face detection, whatever ML, it can do that, and it all runs in this super tiny package. And part of the key thing here, which enables the system, is the Macronix Flash, actually. So what we're doing with these new devices is that they actually execute the model in place off of Macronix Flash. This allows us to more or less kind of make a combined memory architecture where we load the model into a particular flash region that's then memory mapped into the CPU. And then based on that, the AI accelerator on board is actually able to go over the OctoSpy bus and grab the model data as it's doing inference. And then it'll use the internal SRAM to actually hold the model outputs of the weight multiplies and et cetera. And this allows it to very, very quickly execute a model at about, for this guy, it's about 200 megabytes a second. But we have a higher end model called the OpenMV N6, where we're also using Macronix Flash with the new STM32 N6, which is another new microcontroller with an AI accelerator on it, about 600 gigaops. And that one features a 400 megabytes a second bus to the same Macronix Flash to execute a model in place off of the Flash, then do the inference, keep the results in internal SRAM, and gives you the ability to really do high-end computer vision AI algorithms on a very, very low power device. And so it's super exciting that we're able to do this now. and that we really have the flash chips that offer the performance necessary to execute these models in place off of them. Sorry, that was a whole mouthful.
Yeah, it really is, and you know, I think, you know, I've seen the demo, your demo, and you have a fantastic product, and the size of it is just amazing. You know, you can never imagine the level of functionality that you can achieve in such a small form factor, and I think hats off also to companies like Elif that can produce these SoCs that are very powerful, very low power, and are spot on in terms of you know, addressing these AI applications.
Yeah, yeah, and so you know, we're excited that we're able to do this. It's quite how do I say? So there's been a huge technical roadmap and a lot of things that we've had to conquer to get to this point. But being able to execute the model in Flash is really, really important to us because, frankly, you know, the amount of SRAM on this chip is not enough to store a model in it. So, for example, if we want to run a YOLO V2 or, well, let's say YOLO V5 nano model, a small model, which is about 10 megabytes in size, you would have to allocate and put that 10 megabyte model in SRAM. And that's very, very challenging. Like if you look for any microcontroller, nowadays, no one's going to have 10 megabytes of flash built into the device that gives you any throughput. So you have to have these models off chip, and you have to be executing them in place. And so it's awesome to have access to the OctoSpy bus, which, you know, this is our first time actually playing with it. I know that this has existed for a while, but we haven't ever, there wasn't never really a need to have this much performance on the bus, but now it's cool that we're able to leverage AI accelerators and actually put this, you know, performance to use.
Mm-hmm. Yeah, absolutely. I mean, I think OctoFlash is very popular in automotive, where instant on is important, and that's where performance, it's driven, you know, it's been performance driven in that market. But to see it actually applied to, discovered and applied to, you know, AI applications like yours is pretty exciting. Like I said, it gives us a new avenue for growth.
Yeah, and that was for GUIs, right? For automotive before, it's like the infotainment clusters and et cetera.
More boot, you know, just boot code. You know, be able to boot very quickly, and then, you know, if they're doing OTA, and then they need to reboot the system, or if there's some error and they need to reboot, and they need to do it very quickly. So it's a critical requirement. And
understood.
Yeah.
So I think it's time I should show you a demo of what we're able to do with this kind of flash, and kind of give the audience what this show the audience what this unlocks. So I'm going to demo right here. This is the OpenMV N6. It's a little bit, it's more powerful than the smaller camera I showed you, but it has a pretty cool sensor here, which is called the FLIR boson. And so this is a thermal camera, which lets you kind of see heat. The benefit, though, is that it demos really nicely and it looks cool. So we're going to do that for this reason. Anyway, so let me boot up our software and give everyone a show. Just give it a sec. Okay. So let me share right here. Okay, so what we've got going on here, this is OpenMV IDE. And so this is our desktop software, which allows you to program the OpenMV cam. And we're running the wrong script. Here we go. Okay. And so the OpenMV cam, it's a system that runs something called MicroPython. What we've done is we've taken a normal bare metal microcontroller, and it has an RTOS called the MicroPython virtual machine. And this lets you run Python scripts on board. The benefit of this is that you can quickly change the behavior of a system. For example, I can comment out this line of code right here, hit run, and now the system is running a brand new script that has totally changed its behavior via commenting out one line. So very, very powerful. And what we do in order to put models on board the system is we actually have a data structure called the ROM file system. And this allows us to basically create a It's imagine a linear file system record, so you can do folders, files, file names, all that great stuff, and it's all concatenated and creates a linear file system that that can basically be flashed to that can be written to flash, where each file, each record is aligned by 16 bytes and then fully present. Unlike the FAT file system, for example, you can put that on flash, but the FAT file system, when you store files using FAT, they get scrambled because the chunks of the file can be reordered by the file allocation table. And so for ML acceleration, it's very important that the model itself is fully stored as one giant vector, one giant record without any breaks in it. This is what allows then an accelerator to execute that in place. Anyway, so using our code, and this is all that's required for the user at least. There's a lot, of course, going on in the background, lots of C code and other things that we've written for people. This allows you to execute a YOLO V5 model and kind of do person detection. And so as I move away, you can kind of see me here. Yeah, we're able to show off what it looks like for doing human person detection using a thermal camera.
Wow, it's amazing.
Yeah, thank you. And so what's going on here is that inferencing is running off of a Macronix flash right now. So each frame that we're processing, the neural network accelerator is directly going over the OS5 bus at 200 megahertz with DDR speed, so 400 megabytes a second. And it is pulling the weights off of the Octos 5 flash and executing the model and returning results and streaming that video to the computer. And to note, we were actually quite capable of doing more than 12 FPS. So the reason it's slow right now is that we are not using the GPU to recolor. So once I disable this call, that was all CPU. We're able to actually hit closer to 34 frames a second for handling this. So you can see that speed up quite quickly, right?
Mm-hmm.
And then finally, we're actually able to go even faster than that. There is a load that is presented by having the microcontroller stream to the computer. And so realistically, for this model, we're able to actually hit about 40 plus frames a second or so. And probably we should be able to go even faster once we optimize the system. Anyway, the model that we're executing right now is a YOLO V5 tiny model. Nano model. And so this one is about 4 megabytes in size. And so the neural network accelerator is pulling that model off flash and executing it in place. And it's able to, and this is again, it's a couple, like, I think the tiny is somewhere on the small is somewhere on the order of 40 million multiplied accumulates. And so it is pulling all those weights dynamically off the flash to execute this model. Anyway, the important thing to show here is that this technology works and it's ready and it's operational today, which is so cool. It's not theoretical.
Yeah, that's really cool.
Anyway. No, so I think that's a good enough demo for the folks. It's interesting to see this stuff though and see how it's enabled and it's here.
And again, in such a small form factor, it's amazing.
So I think you guys have plans for the future. Like you're not just going to stop at OctoSpy at 8 bits. Like where are things going? Where do you see the evolution happening, Jim?
Yeah, I think beyond just octal, I think what we're starting to see now is support for dual octal. So they have basically a replicated dual octal interface to achieve upwards to 800 to even a 1 gigabyte per second. So we can support on an octal device, we can support up to 250 megahertz DDR, and so that would give you 500. And then if you extrapolate that to 2, you get 1 gigabyte, right? and where the market right now is 800. But the SoC vendor has to support a 250 megahertz interface. So, but in terms of where things are heading, I would say they're heading that way. And then I think probably the voltages are going to drop to 1.2 volt. But I think in the near term, it'll be a dual octal kind of configuration. And then I think probably it'll evolve to a single i16, memory device that will not have all the signals, all the control signals replicated, and the addressing will be more efficient.
I've heard that we actually have that on the OpenMV N6. So it has this thing called a HexaSPI interface, actually. And so that's 16 bits with just one clock signal, one CS line, and then a data strobe. And then it has 16 bits for the rest. And they actually reuse the same standard JDEC form factor where they, the what is it, the 5x6 millimeter package size with the 25 balls, I guess 24 balls on the bottom.
Right.
They pretty much fit the 16-bit bus there. As I said, a clock, a data strobe, and I guess maybe it's 2 data strobes. I think. Yeah, I think it's 2 data strobes because you can do byte addressing, and then you just power supply lines, and they fit that all in the same package. Use up every single pin, but they were able to, cleverly though, basically get 16 bits onto the same package. Yeah. Is that something that Macronix is looking at, or are you guys doing dual octals? It's like a separate 2-die situation.
No, absolutely. That's exactly what we're starting to target. Think for application. You take, for example, smart glasses. Smart glasses are very space constrained, and that's right now they're using dual WLCSP type packages. But I think we're gonna see a requirement for a single package like what you're describing.
Okay.
Yeah.
Gotcha. And so, yeah, I mean, before we go, like, just what are the kind of opportunities and big, you mentioned smart glasses, like, where do you see this technology going in the future, Jim?
Oh my God. I mean, it's really just, again, ubiquitous. I mean, I think if you look at the industrial market, for example, there are these opportunities to place, your product, right? To place them everywhere, so that they can serve as the eyes and ears of a manufacturing plant. If you're looking, for example, at meters or displays, sure, you could have someone walk around and look at them, but why not apply another layer to your product, say, and say notify an operator that there's a problem if the visual falls outside of a range. I mean, to me, just in the industrial market, it's there's so many different applications it can be applied towards.
So. Yeah, no, absolutely. And I thought that before we go, I should give a demo of what it looks like for the small camera I showed off. So the thermal was the OpenMV N6, which is our higher end system. And so this is what that tiny quarter-sized camera is able to do. So we're getting about 16 frames a second streaming to the computer, running a YOLO V5 model on board. This, by the way, is also executing your, executing in place off the Macronix flash chip. The data bus though is only 200 megabytes a second versus 400 of the N6. And then if we disable the load of streaming to the computer, we're actually doing closer to 28 frames a second. So it's able to do a pretty good job, as I said, 30 frames a second to show a YOLO model. One thing I wanted to talk about with these things before we get off is just the kind of applications that are enabled more of this. As you mentioned, smart glasses. I think it'd be good for the audience to know that these camera systems really will bring about a. So the model's not too good, so it can't detect me when I'm this close to it. Okay, there, it's better now. Yeah, this is the FLIR. This model was trained on people walking on the street. versus people sitting in chairs. So it struggles when you're not when you're sitting down versus standing up and walking around. But no, I wanted to talk about was just to give the audience some idea. All of these systems solve a fundamental problem, which is the need for power. Being able to have AI on the go and being able to work with companies like Macronix allows us to build AI cameras that can run on batteries. And so fundamentally, they're low power, able to be placed anywhere, able to communicate and send data to the cloud, and aren't constrained to be plugged into a wall anymore.
Exactly. Yeah. And it just, I mean, it kind of goes beyond. It's basically it'll go as far as your imagination can imagine.
Mm-hmm. And it hopefully primes. I think it sets the stage for a huge growth in the number of flash chips, and I guess these devices that are going to be in the world. Like our thought here is, once you have a device that, again, fits in a package this big for AI and ML, I mean, seriously, it's like it's tiny, right? Once you got this guy, yeah, right. Just put it in your eye. No, I mean, once you have things that are this small, though, it really does open up the idea of you can build cameras and have these become ubiquitous as a smoke alarm. The ability to have it just put into a facility, monitoring or counting whatever you need. That's kind of where we see this technology going. That these low power IoT devices with being able to execute models in place off flash, which is going to be of extreme importance from now into the future. It enables this future of just I guess an example would be we have some customers who are interested in using these for boring applications like staring at gauges, for example, which is the standard kind of boring IoT application that I think has been around in the ether for a while. But they're still excited about it because being able to put a camera over a gauge that was installed back in the 60s and then digitize that operationally makes their life a lot easier because they
that's exactly it. Yeah. Yeah, it's amazing because it's a good transition of the technology we have today and applying it to older technology that they don't want to retrofit everything, but it's a great solution.
Oh yeah. No, I mean, well, for them, these problems are not. There's legal issues. If it's not broken, don't fix it.
Yeah.
Kind of thing. And then when you're talking about big industrial systems, you really do have to talk about money because if you turn off something to replace a valve, and you have to do downtime because safety factors and other various things, that replacement needs to be worth its weight in gold. Basically.
And certifications. A lot of the stuff is certified. Mm-hmm. It's in place, and they have very long product life cycles, and they don't want to replace it.
Yeah.
Yeah.
But you also have other applications, as I mentioned, being ubiquitous, where there's a lot of people analytics that we see folks wanting to do. And so that example would be these devices being like I guess a case in point would be, let's say you wanted to know the count of foot traffic going in and out of your store. This is a problem to every storefront in the USA.
Yeah.
In the world, really. That is a very, very large install base of devices. Mm-hmm. And so to answer that question, a problem would be how do you install this stuff, right? If it comes down to you're going to have to tear up your walls, you're going to have to put PoE conduit in, you're going to put specialized cameras. They're going to cost a lot of money. You got to put a server rack somewhere, et cetera, et cetera, et cetera. Mm-hmm. You're really looking at a lot of friction, right? Most folks aren't going to want to put a system in place if it's going to cost them that much money. But if you're able to offer instead a battery-powered solution that can just run on 3D batteries, for example, for 5 years, that really changes the game. And that's what these new low-power microcontrollers offer with Macronix's Flash, allowing you to run models on board easily. And being able to put that in the ceiling or et cetera, with no extra wires, connect to the internet and transmit data.
or even, even traffic marketing, on shelves and so forth. You walk by, and we're seeing some demand for that. You walk by and they sense that you're there, and even if you're a male or female, and market in a certain way.
Yeah.
Products that are on the shelf,
Yeah, absolutely.
Yeah.
And I think what will be interesting into the future actually is just the ability to run, like right now with the current accelerators, they do not support LLMs, but ARM just announced their Ethos U85 accelerator, and so we're excited to see, in this coming year, I believe different chip vendors. I think Aleph, for example, they announced beginning of this year that they're going to be supporting the U85 in silicon. And that's going to enable some really cool stuff where we can combine that with your flash, hopefully by 16 at this point, because we're going to need the extra performance, and really do stuff like enabling the first LLM to run in a package this small. Of course, it's probably going to need to be dumbed way down. There's definitely no way you're fitting 100 gigabytes. How big are the models? I think
it'll be optimized. It'll be optimized. No doubt about it.
Yeah, no doubt about it. But I think the holy grail may be coming soon, where we might be able to have a camera in this size that would enable folks to be able to point an object at an image, and it would give you a summary of what's happening in that image, like a text message.
And if you look at our products, the demand for density increases. This is a good example of why or how these products evolve and how density evolves, right? So we're going to need to have 1, 2, 4, maybe 8 gigabit. We announced a 3D architecture, which is we're the only ones doing it, and allows for this density. Trying to say this memory density stacking, so you can have much more density in a smaller form factor. And
yeah, absolutely. I think if we hold on,
that's what's going to be driving it. It's going to be LLMs, it's going to be transformers, transformer models and so forth.
No, absolutely, because I really would not know what you're going to do otherwise with what do you need 1 gigabyte of data for? But here's the application.
Maybe
there's going to be a challenge with the RAM component, because we're going to run out of that in the same form factor. But maybe it's possible for researchers to build LLM models that are not just hungry on, well, I guess they can be more hungry on the weights and less hungry on the tensor arena, because I guess while it's executing, right, it doesn't necessarily need to maintain a huge amount of context. Right, as it's going through, you just need more weights as it's executing the layers of the model, and so yeah, there's actually, we could see in the future, and in maybe a couple of years, that someone actually pulls this off, and they're actually able to get a model, let's say in a gigabyte in size on one of these guys, and we can make a camera that can really understand the world with the same level of intelligence we have.
I'm looking forward to that.
Yeah. Anyway, it's not here now. What we've got currently is everything from before ChatGPT, so 2022 and previous, but the future's coming soon.
Sounds good.
Anyway, thank you, Jim. I'll let you go now.
Yeah, thank you. I really appreciate it. Thank you.
Okay. All right.
Good talking to you.
Bye-bye.
Bye.